So hello everyone and welcome to NEETOPEDIA. Today we'll be starting chapter 12 Atoms of class 12th Physics. So let's get started. Chapter 12 Atoms. 12.1 Introduction. By the 19th century, enough evidence had accumulated in favor of atomic hypothesis of matter. In 1897, the experiments on electric discharge through gases carried out by English physicist J.J. Thomson revealed that atoms of different elements contain negatively charged constituents that are identical for all atoms. However, atoms on whole are electrically neutral. Therefore, an atom must also contain some positive charge to neutralize the negative charge of the atoms. But what is the arrangement of positive charge and the electrons inside the atom? In other words, what is the structure of an atom? The first model of atom was proposed by J.J. Thomson in 1898. According to this model, the positive charge of the atom is uniformly distributed throughout the volume of the atom, and the negatively charged electrons are embedded in it like seeds in a watermelon. This model was picturesquely called plum pudding model of an atom. However, subsequent studies on atoms, as described in this chapter, showed that the distribution of the electrons and positive charges are very different from that proposed in this model. We know that condensed matter and dense gases at all temperatures emit electromagnetic radiations, in which a continuous distribution of several wavelengths is present. Though with different intensities, this radiation is considered to be due to oscillation of atoms and molecules governed in the interaction of each atom or molecule with its neighbors. In contrast, light emitted from rarefied gases heated in a flame or excited electrically in a glow tube, such as familiar neon sign or mercury vapor light, has only certain discrete wavelengths. The spectrum appears as series of bright lines. In such gases, the average spacing between atoms is large. Hence, the radiation emitted can be considered due to individual atoms rather than because of interactions between atoms or molecules. In the early 19th century, it was also established that each element is associated with a characteristic spectrum of radiation. For example, hydrogen also is the simplest of all elements known. We shall consider the spectrum in detail in this chapter. Ernst Rutherford, a former research student of J.J. Thomson, was engaged in experiments on alpha particles emitted by some radioactive elements. In 1906, he proposed a classic experiment of scattering of these alpha particles by atoms to investigate the atomic structure. This latter was performed around 1911 by Hans Geiger and Ernst Madison, who was 20-year-old student and had not earned his bachelor's degree. The details are discussed in section 12.2. The explanation of the results led to the birth of Rutherford's planetary model of an atom. According to this, the entire positive charge of Rutherford's nuclear model was a major step towards how we see the atom today. However, it could not explain why atoms emit light of only discrete wavelengths. How could an atom as simple as hydrogen, consisting of a single electron and a single proton, emit a complex spectrum of specific wavelengths? In the classical picture of an atom, the electron revolves around the nucleus much like the way planet revolves around the sun. However, we shall see that there are some serious difficulties in accepting such model. 12.2 Alpha particle scattering and Rutherford's nuclear model of an atom. At the suggestion of Ernst Rutherford in 1911, H. Geiger and E. Madison, as shown in figure 12.1, they directed a beam of 5.5 mega-electron volt alpha particles emitted from a bismuth 214 radioactive source at a thin metal foil of gold. Figure 12.2 shows the schematic diagram of this experiment. Alpha particles emitted by a bismuth radioactive source was collimated into a narrow beam by the passage through lead bricks. The beam was allowed to fall on a thin foil of gold of thickness 2.1 into 10 to the power minus 7 meter. The scattered alpha particles were observed through a rotable detector consisting of zinc sulfide screen and a microscope. The scattered alpha particles, on scattering the sound, produced brief light flashes angle of scattering. A typical graph of the total number of alpha particles scattered at different angles in a given interval of time is shown in figure 12.3. The dots in this figure represent the data points, and the solid curve is the theoretical prediction based on the assumption that the target atom has a small, dense, positively charged nucleus. Many of the alpha particles pass through the foil. It means that they do not suffer any collision. Only about 0.14% of the incident alpha particles scatter by more than 1 degree, and about 1 in 8,000 deflect by more than 90 degrees. Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. This force could be provided if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. Then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. This agreement supported the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of the nucleus. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus, with the electrons some distance away. The electrons would be moving in orbits about nucleus just as the planets do around the sun. Rutherford's experiment suggested the size of the nucleus to be about 10 to the power minus 15 meter to 10 to the power minus 14 meter. From the kinetic theory, the size of an atom was known to be 10 to the power minus 7 meter, about 10,000 to 1 lakh times larger than the size of the nucleus. Thus, the electrons would seem to be at a distance from the nucleus of about 10,000 to 1 lakh times the size of the nucleus itself. Thus, most of an atom is empty space. With the atom being largely empty space, it is easy to see why most alpha particles go right through the thin metal foil. However, when alpha particle happens to come near a nucleus, the intense electric field will scatter it through a large angle. The atomic electrons, being so light, do not appreciably affect the alpha particles. The scattering data shown in figure 12.3 can be analyzed by employing Rutherford's nuclear model of an atom. As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering during their passage through it. Therefore, computation of the trajectory of an alpha particle scattered by a single nucleus is enough. Alpha particles are nuclei of helium atoms and therefore carry 2 units to each nucleus. The magnitude of this force is F is equal to 1 upon 4 pi epsilon naught into 2e into Ze upon r square, where r is the distance between the alpha particle and the nucleus. The force is directed along the line joining the alpha particle and the nucleus. The magnitude and direction of the force of an alpha particle continuously changes as it approaches the nucleus and recedes away from it. 12.2.1 Alpha particle trajectory. The trajectory traced by an alpha particle depends on the impact parameter b of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. A given beam of alpha particle has a distribution of impact parameters b so that the beam is scattered in various directions with different probabilities. It is seen that an alpha particle close to the nucleus suffers large scattering. In case of head-on collision, the impact parameter is minimum and the alpha particle rebounds back. For a large impact parameter, the alpha particle goes nearly undeviated and a small deflection. The fact that only a small fraction of the number of incident particles rebound back indicates that the number of alpha particles undergoing head-on collision is small. This in turn implies that the mass and positive charge of the atom is concentrated in a small volume. Rutherford scattering, therefore, is a powerful way to determine upper limit to the size of the nucleus. I'm skipping this example 12.1, 12.2 for you to solve it later, or you can pause the video and solve it right now. 12.2.2 Electron orbits. The Rutherford nuclear model of the atom, which involves classical concepts, picture of the atom as an electrically neutral space consisting of very small, massive and positively charged nucleus at the center surrounded by revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction Fe between the revolving electrons and the nucleus provides a requisite centripetal force Fc to keep them in their orbits. Thus, for a dynamically stable orbit in a hydrogen atom, Fe is equal to Fc, which implies that E square upon 4 pi epsilon naught r square is equal to mv square upon r. Thus, the relation between the orbit radius and the electron velocity is r is equal to E square upon 4 pi epsilon naught mv square. The kinetic energy and electrostatic potential energy of the electron in hydrogen atoms are K is equal to half mv square is equal to E square upon 8 pi epsilon naught r, and U is equal to minus E square upon 4 pi epsilon naught r. The negative sign in U signifies that the electrostatic force is in the minus r direction. Thus, the total energy E of the electron in a hydrogen atom is E is equal to K plus U, which is equal to E square upon 8 pi epsilon naught r minus E square upon 4 pi closed orbit around the nucleus. I'm skipping example 12.3 for you to solve it later, or you can pause the video and solve it right now. 12.3 Atomic Spectra. As mentioned in section 12.1, each element has a characteristic spectrum of radiation which it emits. When an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitter radiation has a spectrum which contains certain specific wavelengths only. A spectrum of this kind is termed as emission line spectrum, and it consists of bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown in figure 12.5. The study of emission of line spectra of a material can therefore serve as a type of fingerprint for identification of the gas. When white light passes through a gas and we analyze the transmitted light through a spectrometer, we find some dark lines in the spectrum. These dark lines correspond precisely to the wavelengths which were found in the emission line spectrum of the gas. This is called the absorption spectrum of the material of the gas. 12.3.1 Spectral lines. We might expect that the frequencies of the light emitted by a particular element would exhibit some regular pattern. Hydrogen is the simplest atom and therefore has the simplest spectrum. In the observed spectrum, however, at first sight, there does not seem to be any resemblance of order or regularity in spectral lines, but the spacing between the lines within certain sets of higher spectrum decreases in a regular way. Each of these sets is called spectral series. In 1885, first such series was observed by Swedish school teacher Johann Jacob Balmer in visible region of the hydrogen spectrum. This series is called Balmer series. The line with the found a simple empirical formula for the observed wavelengths. 1 by lambda is equal to r into 1 by 2 square minus 1 upon n square. Where lambda is the wavelength, r is a constant called the Rydberg's constant, and n may have integral values 3, 4, 5, etc. The value of r is 1.097 into 10 to the power 7 per meter. This equation is also called Balmer formula. Taking n is equal to 3 in equation, we obtain the wavelength of H alpha line equals to 656.3 nanometer. For n is equal to 4, one obtains the wavelength of H beta line, etc. For n is equal to infinity, one obtains the limit of the series. At lambda is equal to 364.6 nanometer, this is the shortest wavelength in the Balmer series. Beyond this limit, no further distinct lines appears. Instead, only a faint continuous spectrum is seen. Other series of spectra for hydrogen are subsequently discovered. These are known after the discoveries as Lyman, Paschen, Brackett and Pfund series. These are represented by the formula. Lyman series is 1 upon lambda is equal to r into 1 by 1 squared minus 1 upon n squared. Pfund series is 1 upon lambda equals to r into 1 upon 5 squared minus 1 upon n squared. The Lyman series is in the ultraviolet, the Paschen, Brackett and Pfund series are in the infrared region. The Balmer formula may be written in terms of frequency of the light, recalling that V is equal to nu lambda, or 1 by lambda is equal to nu upon c. Thus the equation becomes nu is equal to Rc into 1 upon 2 square minus 1 upon n square. There are only a few elements whose spectra can be represented by simple formulas. Equations are useful as they give the wavelengths that hydrogen atoms radiate or absorb. However, these results are empirical and do not give any reasoning why only certain frequencies are observed in the hydrogen spectrum. 12.4 Bohr model of the hydrogen atom. The model of the atom proposed by Rutherford assumes that the atom consisting of a central nucleus and revolving electron is stable, such like the sun-planet system, which the model imitates. However, there are some fundamental differences between the two situations. While the planetary system is held by gravitational force, the nucleus-electron system, being charged object, interact by Coulomb's law of force. We know that an object which moves in a circle is being constantly accelerated, the acceleration being centripetal in nature. According to classical electromagnetic theory, an accelerating charged particle emits radiation in form of electromagnetic waves. The energy of an accelerating electron should therefore continuously decrease. The electron would spiral inward and eventually fall into the nucleus. Thus, an atom cannot be stable. Further, according to the classical electromagnetic theory, the frequency of electromagnetic waves emitted by the revolving electron is equal to the frequency of revolution. As the electrons spiral inwards, the angular velocities and the frequencies would change continuously. And so, I'm skipping example 12.4 for you to solve it later, or you can pause the video and solve it right now. It was Niels Bohr who made certain modifications in this model by adding the ideas of the newly developing quantum hypothesis. Niels Bohr studied the Rutherford's laboratory for several months in 1912. He was convinced about the validity of Rutherford's nuclear model, faced with the dilemma as discussed above. Bohr in 1913 concluded that in spite of the success of electromagnetic theory in explaining large-scale phenomena, it could not be applied to the processes on the atomic scale. It became clear that a fairly radical departure of the established principle of classical mechanics and electromagnetism would be needed to understand the structure of atom and the relation of atom spectra to atomic structure. Is out. Number 1. Bohr's first postulate was about an electron in an atom would revolve in certain stable orbits without the emission of radiant energy, contrary to the predictions of the electromagnetic theory. According to this postulate, each atom has certain definite stable states in which it can exist, and each possible state has definite total energy. These are called the stationary states of the atom. Number 2. Bohr's second postulate defines these stable orbits. This postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h upon 2 pi, where h is the Planck's constant equal to 6.6 into 10 to the power minus 8, where E initial and E final are the energies of initial and final states, and E initial is greater than E final. For a hydrogen atom, the equation gives the expression to determine the energies of different energy states. But then, this equation requires the radius of an electron orbit. To calculate our Bohr's second postulate about the angular momentum of the electron, the quantization condition is used. The angular momentum L is given by L is equal to mvr. Bohr's second postulate of quantization says that the allowed values of angular momentum are integral multiples of h upon 2 pi. L is equal to mvr is equal to nh upon an integer. Rn is the radius of nth possible orbit and Vn is the speed of a moving electron in the nth orbit. The allowed orbits are numbered 1, 2, 3 according to the values of n, which is called the principal quantum number of the orbit, where Vn is equal to E upon under root 4 pi epsilon naught mRn. We're combining it with the above equation, which we can get Rn is equal to n squared upon m into h upon 2 pi whole square into 4 pi epsilon naught e square. The equation depicts that the orbital speed in the nth orbit falls by a factor of n. The size of the innermost orbit, that is n equals to 1, can be obtained as r is equal to h square epsilon naught upon pi me square. This is called the Bohr radius, represented by the symbol A0. Thus, A0 is equal to h square epsilon naught upon pi me square. Substitution of values of h, m, epsilon naught and e gives A0 equals to 5.29 into 10 to the power minus 11 meter. It can also be seen that the radii of the orbits increase as n is square. The total energy of the electron in the stationary states of the hydrogen atom can be obtained by substituting the value of orbital radius in equation 12.4 as En equals to m minus m e to the power 4 upon 8 n square epsilon naught square h square. Substituting the values, it yields that En is equal to minus 2.18 into 10 to the power minus 18 upon n square joule. Atomic energies are often expressed in electron volts rather than joules. Since 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, it can be written as En is equal to minus 13.6 upon n square electron volt. The negative sign of the total energy of an atom moving in an orbit means that the electron is bound with the nucleus. Energy will thus be required to move the electron from the hydrogen atom to a distance infinitely away from its nucleus. The derivation of equations involves the assumption that the electronic orbits are circular, though orbits under inverse square force are generally elliptical. However, it was shown by German physicist Arnold Sommerfeld that when the restriction of circular orbit is relaxed, these equations continue to hold even for elliptic orbits. I am skipping example 12.5 for you to solve it later, or you can pause the video and solve it right now. 12.4.1 Energy levels. The energy of an atom is the least when its electron is revolving in an orbit closest to the nucleus, that is, one for which n is equal to 1. For n equals to 2, 3 and so on, the absolute value of energy E is smaller. Hence, the energy is progressively larger in the outer orbits. The lowest state of the atom, called the ground state, is that of the lowest energy. With the electron revolving in the orbit of the smallest radius, the Bohr radius A0, the energy of this state, E1 is equal to minus 13.6 electron volt. Therefore, the minimum energy required to free the electron from the ground state of a hydrogen atom is 13.6 electron volt. This is called the ionization of the hydrogen atoms are in ground state. When a hydrogen atom receives energy by process such as electronic collisions, the atom may acquire sufficient energy to raise the electron to higher energy states. The atom is then said to be in excited state. For n is equal to 2, the energy E2 is minus 3.40 electron volt. It means that the energy required to excite an electron in hydrogen atom to its first excited state is an energy equal to E2 minus E1 is equal to minus 30 minus 3.40 electron volt minus 13.6 electron volt, which is equal to 10.2 electron volt. Similarly, E3 is equal to minus 1.51 electron volt, given in figure 12.8. The principal quantum number n labels the stationary states in the ascending order of energy. In this diagram, the highest energy state corresponds to n is equal to infinity and has an energy of 0 electron volt. This is the energy of atom when the electron is completely removed from the nucleus and is at rest. Observe how the energies of excited states come closer and closer together as n increases. 12.5. The line spectra of the hydrogen atom. According to the third postulate of Bohr's model, when an atom makes a transition from higher energy state with quantum number Ni to lower energy state with quantum number Nf, the difference of energy is carried away by a photon of frequency nu if, such that h nu if is equal to Eni minus Enf. Or nu if is equal to me to the power 4 upon 8 epsilon naught square h cube into 1 upon nf square minus 1 upon ni square. This equation is the Rydberg formula for the spectrum of hydrogen atom. In this relation, we take nf equals to 2 and ni is equal to 3, 4, 5 and so on. It reduces to form similar for Balmer series. The Rydberg constant R is readily identified to be R is equal to me to the power 4 upon 8 epsilon naught square h cube into c. If we insert the values of the various constant, we get R is equal to 1.03 into 10 to the power 7 per meter. This is a value very close to the value obtained from the empirical Balmer formula. This agreement between theoretical and experimental values of Rydberg constant provided a direct and striking information of the Bohr's model. Since both Nf and Ni are integers, this immediately shows that in transitions between different atomic levels, light is radiated in various discrete frequencies. For hydrogen spectrum, the Balmer formula corresponds to Nf equals to 2 and Ni is equal to 3, 4, 5, etc. The results of the Bohr's model suggested the presence of other series spectra for hydrogen atom, those corresponding to transitions resulting from Nf equals to 1 and Ni equals to 2, 3, etc. Nf is equal to 3 and Ni is equal to 4, 5, etc. and so on. Such series were identified in the course of spectroscopic investigations and are known as Lyman, Barber, Bastian, Brackett and Pfund series. The electronic transitions corresponding to this series is shown in figure 12.9. The various lines in the atomic spectra are produced when electrons jump from higher energy state to a lower energy state and photons are emitted. These spectral lines are called emission lines. But when an atom absorbs a photon that has precisely the same energy needed by the electron in lower energy state to make transitions to a higher energy state, the process is called absorption. Thus, if photons with continuous range of frequencies pass through a rarefied gas and then are analyzed with a spectrometer, the series of dark spectral absorption lines appear in the continuous spectrum. The dark lines indicate the frequencies that have been absorbed by the atoms of the gas. The explanation of the hydrogen atom spectrum provided by Bohr's model was a brilliant achievement, which greatly stimulated progress towards the modern quantum theory. In 1922, Bohr was awarded Nobel Prize in Physics. I'm skipping example 12.6 for you to solve later, or you can pause the video and solve it right now. 12.6. De Broglie's explanation of Bohr's. 12.6 de Broglie's explanation of Bohr's second postulate of quantization. Of all the postulates, Bohr made it in his model of atom perhaps the most puzzling in his second postulate. It states that the angular momentum of an electron orbiting around the nucleus is quantized. Why should the angular momentum have only those values that are integral multiples of h upon 2 pi? The French physicist Louis de Broglie explained this puzzle in 1923, 10 years after Bohr proposed his model. We studied in chapter 11 about the de Broglie hypothesis that material particles such as electron also have a wave nature. C.J. experimentally verified the wave nature of electrons. In 1927, Louis de Broglie argued that the electron in its circular orbit, as proposed by Bohr, must be seen as a particle wave in analogy to waves traveling on a string. Wave particles too can lead to standing waves under resonant conditions. From chapter 15 of class 11 physics textbook, we know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have nodes at the ends and form the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back one wavelength, two wavelength, or any integral multiple of the wavelength. 2 pi Rn is equal to n lambda, where n is equal to 1, 2, 3 and so on. Figure 12.10 illustrates a standing wave particle on a circular orbit for n is equal to 4. That is 2 pi Rn is equal to 4 lambda, where lambda is the de Broglie wavelength of the electron moving in nth orbit. From chapter 11 we have lambda equals to h upon p, where p is the magnitude of the electron's momentum. If the speed of the electron is much less than the speed of light, the momentum is mvn, where lambda is equal to h upon mvn. We have 2 pi Rn is equal to nh upon mvn, or mvn Rn is equal to nh upon 2 pi. This is the quantum condition proposed by Bohr for the de Broglie hypothesis, provided an explanation for Bohr's second postulate for the quantization of angular momentum of the orbiting electron. The quantized electron orbits and energy states are due to wave nature of the electron, and only resonant standing waves can persist. Bohr's model involving classical trajectory picture correctly depicts the gross features of the hydrogenic atoms. In particular, the frequencies of the radiation emitted or selectively absorbed. This model, however, has many limitations. Some are: number 1, the Bohr model is applicable to hydrogenic atoms. It cannot be extended even to mere 2 electrons such as helium. The analysis of atoms which are more than 1 electron was attempted on the lines of Bohr's model of hydrogenic atoms did not. The formation of Bohr model involves electrical force between positively charged nucleus and electron. This does not include the electrical forces between electrons which necessarily appear in multi-electron atoms. Number 2. While the Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, the model is unable to explain the relative intensities of the frequencies in the spectrum. In emission spectrum of hydrogen, some of the visible frequencies have weak intensities, others strong. Why? Experimental observations depict that some transitions are more favored than others. Bohr's model is unable to account for the intensity variations. Bohr's model represents an summary. Number 1. Atom as a whole is electrically neutral and therefore contains equal amount of positive and negative charges. Number 2. In Thomson's model, an atom is a spherical cloud of positive charges with electrons embedded in it. Number 3. In Rutherford's model, most of the mass of the electron and all its positive charge are concentrated in a tiny nucleus and the electrons revolve around it. Number 4. Rutherford's nuclear model has 2 main difficulties in explaining the structure of an atom. It predicts that atoms are unstable because the accelerated electrons revolving around the nucleus must spiral into the nucleus. This contradicts the stability of matter. It cannot explain the characteristic line spectra of atoms of different elements. Number 5. Atoms of the most elements are stable and emit characteristic spectrum. The spectrum consists of a set of isolated parallel lines termed as line spectrum. It provides useful information about the atomic structure. Number 6. The atomic hydrogen line emits spectrum consisting of various series. The frequency of any linear series can be represented as a difference of the two terms: Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series. Number 7. To explain the line spectra emitted by atoms as well as the stability of atoms, Niels Bohr proposed a model for hydrogenic atoms. He introduced 3 postulates and laid the foundations of quantum mechanics. In a hydrogen atom, an electron revolves in the certain stable orbits without the emission of radiant energy. B. Atoms. The stationary orbits are those for which angular momentum is some integral multiple of h upon 2 pi. That is, L is equal to nh upon 2 pi, where n is an integer called the principal quantum number. Number 3. The third postulate states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy, or E final. Number 8. As a result of quantization condition of angular momentum, the electron orbits the nucleus in only specific radii. For a hydrogen atom, it is given by Rn is equal to n square upon m into h upon 2 pi whole square into 4 pi epsilon naught upon E square. The total energy is also quantized as En equals to 13.6 electron volt upon n square, where n is equal to one state is called ground state. In hydrogen atom, the ground state energy is minus 13.6 electron volts. The higher values of n correspond to excited states. Atoms are excited to these higher states by collision with other atoms or electrons or by absorption of a photon of right frequency. Number 9. De Broglie's hypothesis. Points to ponder. Number 1. Both Thomson as well as Rutherford's model constitute an unstable system. Thomson's model is unstable electrostatically, while Rutherford model is unstable because of electromagnetic radiation of orbiting electrons. Number 2. What made Bohr quantize angular momentum and not some other quantity? Note that h has dimensions of angular momentum, and for circular orbits, angular momentum is a very relevant quantity. The second postulate is then so natural. Number 3. The orbital picture of Bohr's model of hydrogen atom was inconsistent with the uncertainty principle. This was replaced by modern quantum mechanics, in which Bohr's orbits are regions where Bohr's model include only one quantum number n. The new theory called quantum mechanics supports Bohr's postulate. However, in quantum mechanics, a given energy level may not correspond to thus one quantum state. For example, a state is characterized by 4 quantum numbers n, l, m, and s. But for pure Coulomb potential, the energy depends only on n. In Bohr's model, contrary to the ordinary classical expectation, the frequency of revolution of an electron in its orbit is not connected to the frequency of spectral line. The latter in the difference between the orbital energies divided by h. For transitions between large quantum numbers, however, two coincide as expected. Number 7. Bohr's semi-classical model, based on some aspects of classical physics and some aspects of modern physics, also does not provide a true picture of the simplest hydrogenic atoms. The true picture is quantum mechanical affair, which differs from Bohr's model in a number of fundamental ways. But then, if the Bohr's model is strictly correct,